Hello students, today we will discuss one important topic of classical mechanics that is called constraint motion. So first we will discuss what is constraint motion. So constraint motion is when a object is forced or compelled to move in a restricted way due to some obstacles or geometrical restrictions are there. So first we will take one example. So first case, this is a free particle and it is moving in a xyz coordinate. So for free particle, the x can be minus infinity to plus infinity, y is equal to and z is equal to minus infinity to plus infinity. That means it can go anywhere. Its motion is not restricted. But the same particle, if it is confined in a box, so here the particle's motion is restricted uh, to move in this particular box. So here the x will be 0 to a, that means the side of a, and y will be the 0 to b, and the z is equal to 0 to c. That means now this particle is confined to move in this particular rectangular box. Now we will discuss some more examples of constraint motion. So this is a ball, red ball. So this is for this first case, it is moving on a horizontal surface. So because of this surface, because of this geometrical shape, the ball is forced to move along this horizontal direction. Whereas in the second case, the same ball is moving in the inclined plane. So due to its geometrical shape, and the gravitational force is acting here, that is why it is moving in the downward direction. It is not possible for the ball to go in the upward direction. Now the third case, the ball is rolling on the inner surface of a hemispherical ball. So because of these inner surface geometrical shape, the ball is oscillating, and after some time, due to the friction, it will be stopped at this position. Now the fourth example is the oscillation of pendulum. So here, because of this string, the bob is moving in a particular direction. So here the string is the constraint and the motion of the bob is constrained motion. And here the tension is acting on this bob, and because of this tension the bob is forced to move along this particular direction. Now the vibration of a string. So if a body is attached to a spring, so because of this string and because of this restoring force of the string, the body or the object is forced to move along this particular direction. And the last one is vibration of a molecular bonds in a solid material. So in a solid materials, the molecular bonds are like a spring like things, and it is the molecules are forced to move along a particular direction because of these molecular bonds. Now we will discuss what is constraint. So previously we have discussed what is constraint motion. Now we will discuss what is constraint. Constraint is that the surface or curve on which the particle must move. That means the limitations on motion are often called constraints. That means, suppose in this first case, the constraint is the rectangular box. That means because of this rectangular box or the geometrical shape, the ball is forced to move along within this particular box. The second one, the constraint is the horizontal plane. So because of this plane, because of this constraint, the ball is forced to move along this horizontal direction. The third one, the constraint is the inclined plane. Fourth one is the inner surface of the hemispherical ball. So because of these inner surface geometrical shape, the particle is forced to move along this direction, oscillating. Now the fifth one, the constraint, is the inextensible massless string. So because of this string, the bob is oscillating. And the last one, the constraint, is the spring. So because of this spring, the object or the body is forced to move along this horizontal direction. Now, what is the constraint force? So, the forces that the constraining object exerts on the object to make it follow the constraints. That means, what is the nature of the constraint force? The constraint force mainly is due to the weight of the body, or the pressure exerted on the constraint, or some elastic properties of the constraints. So, these are the some constraint forces. Now for first case, the constraint force is the normal reaction force by the wall of the box. That means when the ball is hitting the wall of the box, then for Newton's third law, the if the ball gives the action, then opposite equal and opposite reaction force is applying in the ball by the wall of the box. So because of this reaction force, the ball is forced to move along within this box. The second one, the constant force, is a normal reaction force by the horizontal plane surface. And third one is the normal reaction force by the inclined plane of surface. So the mass, the weight of the body is acting downward, and the normal reaction force is acting upward direction. And the fourth one, the normal reaction force by the inner surface of the hemispherical bowl. And the fifth one, the constant force, is the tension of the string. So because of this tension, so mg of the bob, the weight is acting downward, and the tension of the string is acting upward direction. And the last one, the restoring force by the spring, is the constant force. That means F is equal to minus kx. K is the spring constant. Now we will discuss the constraint equation. So constraint equations are divided into two parts, that is holonomic constraint and non-holonomic constraints. This is based on the velocity factor. That means one is independent of velocity, another is dependent of velocity. So the holonomic constraints can be expressed by a proper equation, and it is connecting to the position of the particles and the time. And most important thing is, this is independent of velocity of the particles. So one example is, that is a bob is oscillating. So here the equation is x square plus y square is equal to L square. So this is a proper equation, x square plus y square is equal to L square, and here only position is related. This is velocity independent equation. So if a particle is or bob is moving in a very slow way, slow velocity, then also the equation is valid. And suppose it is moving in a very faster way, then also it is valid. That means it does not depend how fast the particle is moving. That means the holonomic constant is velocity independent equations or constraints. Next is non-holonomic constraints. So it is a just opposite to the holonomic constant. That means it cannot be expressed by proper equation connecting position of the particles and the time. And the important thing is, it is dependent of velocity of the particles. That means if a gas is kept in a spherical container with radius a, and r is the position vector of gas molecules, then the condition of constraint for motion of a molecule is given by r less than equal to a, or r minus a less than equal to 0. That means the position vector of gas molecule is always less than the radius of the spherical container. Now, depending on the time factor, the holonomic constraint again divided into two factors. One is scleronomic constraints, another is rheonomic constraints. So, scleronomic constraints which do not explicitly depend on time, that means the first equation x square plus y square is equal to L square, that means the bob is oscillating, SHM, simple harmonic motion. So, x square plus y square is equal to L square. Here time is not explicitly involved here. That is why it is an example of scleronomic constraints. And what is the example of rheonomic constraint? Rheonomic constraint means which explicitly depend on time. That means suppose the same pendulum, the effective length L of a simple pendulum varies with time because of change of temperature, then it becomes an example of rheonomic constant. That means L is a function of T. That means x square plus y square is equal to L is a function of T whole square. Now, there is another example of holonomic non-holonomic constraint equation. So here, suppose this is a horizontal plane and here one sphere is fixed, and here on the top of the sphere there is one ball, and the position vector of the ball is x1, y1, z1, and the a is the radius of the sphere. So from spherical polar coordinates, we know that equation of sphere, that is x square plus y square plus z square is equal to a square. That means r square is equal to a square. So r is equal to x I cap plus y j cap plus z k cap. So r square minus a square is equal to 0. That is, this is the holonomic constant equation. So here the equation is r square minus a square is equal to 0. So suppose for another time the ball is here in this position, then also this equation valid, that is r square minus a square is equal to a square. And suppose the ball is here and the position is x3, y3 and z3. So then also this equation is valid, r square minus a square is equal to 0. But after this position, the particle is able to fall off the sphere under the influence of gravity or due to the gravitational force. Then the constant becomes non-holonomic constant. That means in this region here r square minus a square greater than equal to 0. So this is the example of non-holonomic constraints. Now we will discuss some other examples of holonomic constraints. So first is pendulum with fixed length, that I have already discussed. So here the length of the string L connecting to the pendulum to its pivot is constant. So x and y is the represent the position of the pendulum bob in two-dimensional plane. So x square plus y square is equal to L square. So these equation restricts the possible positions of the pendulum, but it does not depend on its velocity or how fast it is moving. The next example is bead on a wire. So suppose a bead is moving in a fixed wire or a circular wire, then x square plus y square is equal to r square, and it is independent of velocity. Third one is the rigid body with fixed distance between 2 points. So suppose there are rigid body where 2 points P1 and P2 are fixed and the distance between these 2 points is D. So let the position vector of 2 points, that is R1 and R2. So R1 minus R2, the mod value is equal to D. So this ensures the distance between the 2 points remain constant during the motion of the body. That means if the rigid body is moving, but the D will be always fixed because it is a rigid body. The fourth one is the object moving on a surface. So if the object is constant to move on a specific sphere, then the constant equation is x square plus y square plus z square is equal to r square. So what is the main factors for holonomic constants? First, this is position dependent, that means it is restricted in the position or generalized coordinate of a system. Second, this is the velocity independent and the integrable factor, that means the constant relations are constant equations are related with the position coordinates only. So the holonomic constraints limit the configuration of the system without directly imposing constraints or how fast the system moves. Now we will discuss the examples of non-holonomic constraints. So first example is rolling without slipping. That means a ball or a wheel, suppose it is rolling without slipping, meaning the velocity at the point of contact with the ground is always zero, and it is a combination of translational and rotational motion where the point of contact is instantaneously at rest. So that means suppose the wheel, the radius of the wheel is r and linear velocity is v and angular velocity is omega, then the non-holonomic constant is v minus r omega is equal to 0. That means it involves the velocity of the system. It is velocity dependent equation. The second one is skating or sliding. So if a vehicle or object is constrained to slide in a certain direction, then the constraint might involve the velocity components relative to the direction of the motions. So in these two cases, the constraints depend on how the system is moving. That means it is velocity dependent factors are there. Now we will discuss the example of scleromic and rheonomic constraints. So first we have already discussed that suppose a simple pendulum is attached with a rigid support. That means this is a rigid support and it is attached with this string, that is L, of length of the string is L, that and it is moving in this YZ plane. So y square plus z square is equal to L square. So here in this equation, time is not explicitly or directly involved. So this is the example of scleromic constraint equation. But in the next case, suppose the motion of the bob in a simple pendulum attached with a rigid support, but this support is oscillating with a frequency omega. That means here this bob is oscillating and this rigid support at a particular point, and this point is also oscillating with a frequency omega. Then y is equal to plus minus y cos omega 0 t whole square plus z square equal to L square. So here t is directly involved. So this is example of rheonomic constraint equation. Or suppose this length is varying with respect to time. That means it changes its length with respect to time due to the temperature. Then y square plus z square is equal to L is a function of t whole square. So this is another example of rheonomic constraint equation. Now we will discuss that what is generalized coordinate. So generalized coordinate is are a set of independent parameters. Here independent term is very important. Independent parameters that can describe the configuration of a system and its motion. That means suppose a particle is moving, a free particle is moving in a three-dimensional space. So we require x, y, z, that is the three coordinates are required to specify the configuration of the system. So for two particles we require 6 coordinates. So for n particles we require 3n number of coordinates. And suppose the m is the equation of constraints. That means the from the 3n coordinates, m is the restrictions we have imposed. So the total number of degrees of freedom or total number of generalized coordinate, that is small n, is equal to 3n minus m. So 3n is the total number of coordinates minus the equation of constraints equal to the number of degrees of freedom and the number of independent parameters required to specify the configuration of the system, that is called generalized coordinate. So the generalized coordinates are usually selected to provide the minimum number of independent coordinates that define the configuration of a system, and the number of degrees of freedom is always equal to the number of generalized coordinate. Now in this first case, the constant equation is, that is the ball is moving in this direction, so r square minus a square is equal to 0. So here for spherical polar coordinates we know that here the xyz is equal to the r theta phi. So here r is in the constant motion, constant equation. So the position of the ball or the sphere can be described by only theta and phi. So here theta and phi are the independent parameters. They are not involved in the constraint motion. So in the constraint equation only r is involved, r parameter, and theta and phi are the independent parameters. So that is why here the number of degrees of freedom is 2 and number of generalized coordinate is also 2. So second case, that is the bob is oscillating in a simple pendulum. So here this is in the two dimensional case, y and z is involved, yz two dimensional. So here y square plus z square is equal to L theta. So for polar coordinates we know that for polar coordinates we require two dimensional system r and theta. So here r is involved in this constraint equation. So here only theta is the, this theta is the independent parameters, and this is also the generalized coordinate, and the degrees of freedom is also in this case 1. So due to the constraints in a system, we can reduce the number of coordinates required to describe its motion, and this is the importance of constraint equations. Now we will discuss the pulley mass system. So this is important for numericals, and this is the, what is the mathematical analysis of constraint motion. So here the L is the length of the inextensible cable, okay, and Z1 and Z2, so displacements of M1 from at instant time, suppose this is a Z1 and Z2 is the dotted line, that is distance between this pulley, center of the pulley to the M2, mass M2. Here M2 is greater than M1. So what is the constant equation? So this is the Z1 plus this is the pi r. So total circumference of the pulley is 2 pi r. R is the radius of the pulley. So the half of the circumference, that is pi r. So here the Z1 plus pi r plus Z2 is equal to the total length. So here Z1 plus Z2 is equal to constant. That means when the Z1 decreases, Z2 is increases its value, and total Z1 and Z2 is constant. So differentiating with respect to time, we get V1 is equal to minus V2, and differentiating again with respect to time, we get A1 is equal to minus A2. Now we will do the write down the equation of motion, that is the M1A1 is acting in the upward direction and M1G in the downward direction. So M1A1 is equal to T minus M1G, and M2A2 is acting upward direction. So M2A2 is equal to M2G minus T. So if we add these two equations, we get M1A1 plus M2A2 is equal to M2 minus M1 into G. And we know that the acceleration of this M1 and M2 is equal and opposite. From this we can get the value of the mass, the acceleration of the M1 and M2 block. Now we will solve some numericals based on this friction and the mass pulley system. So suppose the first problem states that a block of mass m 3 kg is resting on a rough inclined plane of inclination 30 degree as shown in the figure 1.26. This is the free body diagram of block M, and the coefficient of friction between the block and the plane is mu is equal to 0.25. So what is the minimum force should be applied perpendicularly to the plane on the block so that the block does not slip on the plane. So here the condition is mg sin theta greater than mu mg cos theta. So here n equal to f plus mg cos 30, where m is the 3 kg, g is the 10 meter per second square, and theta is the 30 degree. And the second mg sin theta is equal to mu n, and n is again f plus mg cos theta cos 30. So from these two equations we can easily find out the force, that is 34.02 Newton. The second problem states that suppose in this system the bodies have masses m1, m2 and m3, and there is a friction acting between the table and the m1, that is mu. So find the acceleration of the body m2, and here there is one assumption, that is masses of the pulleys and the threads are negligible. So here the constraints equation gives that A1 is equal to, so here A1 is acting in this direction and A2, A3 acting in the opposite direction. So A1 is equal to A2 plus A3 and T is equal to 2T1. So T is acting in the downward direction and this is the upward direction. T is equal to 2T1. So from the Newton's second law we can write m2g minus T1 is equal to m2a2, m3g minus T1 is equal to m3a3, and T minus mu m1g, that is m1a1. So using these 5 equations we can easily solve this A2. This is your assignment. Now thank you all.